In this video, I will show you how initial conditions can lead to particular solutions as opposed to the general solutions that we've been finding so far. Consider example 1. Find the general solution of the differential equation y prime equals 3x squared minus 1. This is a differential equation because of the y prime. Solving this means getting y by itself, so we need to reverse the differentiation. In other words, we must find the antiderivative. And that is the same as finding the integral of 3x squared minus 1. So the solution y is going to equal the integral of 3x squared minus 1 dx. We know how to find this. We will simply integrate each term separately. So y equals. For the first term, we're going to leave the 3 alone. Always leave that first constant by itself. We will do the power rule of integration on the x squared part, where we will increase the exponent by 1, making it x to the third power, and then dividing by that new power. So we have this. Now, the integral of 1 is x. And then we must add the constant of integration. Obviously, the 3's are going to cancel each other out, so we get the general solution y equals x to the third power minus x plus c. Because the constant of integration c can represent any constant, then the function y equals x to the third power minus x plus c represents an entire family of functions depending on the value of c. Here's what the function looks like when c is equal to 0. But if c is equal to 1, we have a vertical translation. Watch how the graph behaves when c is equal to 2, or 3, or 4. What about when c is equal to -1, or -2, or -3, or -4? So we see that the function y equals x to the third power minus x plus c represents a family of infinitely many vertical translations. So far, we've found the general solution of the differential equation, this family of infinitely many vertical translations. But what if we are asked to find the particular solution that passes through the point 2, 4? This new piece of information, this single point on the graph, is called the initial condition, and it will allow us to find c and nail down a particular solution to the differential equation. Here's how. We are given an x, y pair. So when x is 2, y is 4. Let's substitute that information into the general solution. So y will be 4 when x is 2. So we have 2 to the third power minus 2 plus c. But that means 4 is equal to 8 minus 2 plus c. So 4 is equal to 6 plus c. And subtracting 6 from both sides, we have -2 is equal to c. So we have just found the value of c. Substituting that back into the general solution, we have y equals x to the third power minus x minus 2. So instead of a family of infinitely many vertical translations, we have now narrowed it down to one particular solution based on the initial conditions. Graphically, you can see that we have our family of vertical translations, but only one of these vertical translations is going to pass through the point 2, 4. And as we discovered numerically, the function that passes through the point 2, 4 is the one where the value of c is -2. Let's practice our new skills on example 2. Find the general solution of f prime of x equals 1 over x squared, where x is greater than 0. So solving a differential equation like this means, in a way, getting f by itself. So we need to undo the differentiation. In other words, we need to find the antiderivative. And finding the antiderivative means taking the integral of the function. So we're going to do the integral of 1 over x squared dx. Our first step is to rewrite the function to better use the power rule. So this is the same as the integral of x to the negative 2 power dx. The power rule of integration says we should add 1 to the exponent and then divide by the new exponent. So capital F of x will equal x to the negative 1 power, see we've added 1, divided by negative 1. Of course, we must include the constant of integration. So simplifying this a little bit, we have the general solution, capital F of x is equal to negative, because of the negative 1 denominator, 1 over x. All right, x to the negative 1 power drops the variable down to the denominator, and then plus c. So now we have the general solution, that family of infinitely many vertical translations. Let's use the initial condition, f at 1 equals 0, to find the value of the constant and produce a particular solution. This initial condition is telling us that when x is 1, the value of the function is 0. So let's substitute that information into the general equation. So we are saying when x is 1, so that makes this 1 over 1 plus c. The value of the function is 0, so all of this will equal 0. So that will give us 0 is equal to negative 1 plus c. Adding 1 to both sides, we have 1 is equal to c. We have found the value of the constant of integration under these initial conditions. Let's substitute that back into the general solution to come up with a particular solution. So f of x will equal negative 1 over x plus 1. So, given the initial condition, we are able to come up with a particular solution instead of just a family of vertical translations. Let's apply the concept of initial conditions to solve a real-world problem. See if you can hear the initial conditions as I read example 3. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. First, let's find the position function given the height s as a function of time t. Before we go on, we need to take a moment to review the relationship between position, velocity, and acceleration. Given a position function, s at t, the velocity function will be s prime at t, and the acceleration function will be s double prime at t. In other words, velocity is the derivative of position, and an acceleration function is the derivative of velocity. If ever I needed to go in reverse, if I needed to go from acceleration to velocity, I would have to take the integral. If I wanted to go from velocity to position, again, I would have to find the antiderivative. I would have to find the integral. So our quest to find a position function begins with acceleration. We know that the acceleration due to gravity is negative 32 feet per second per second. I'm going to leave off the units for now. The negative is because the acceleration due to gravity is always going to be down. So if I want to go from an acceleration function to a velocity function, I need to take the integral. So the velocity function will equal the integral of negative 32 dt. So the velocity function is negative 32t plus c, the constant of integration. This is the general solution. Let's see if we can use the initial conditions to find c and come up with a particular solution. So we are told that the initial velocity is 64. So this is an initial condition. In other words, s prime at 0, the velocity at time 0, is equal to 64. Let's substitute this information into the general equation. So at time 0, so that means we have negative 32 times 0 plus c. The velocity is 64, so this entire equation will equal 64. Of course, 32 times 0 is just 0, so that immediately gives us that 64 is equal to c. Now we have found the constant of integration that matches these initial conditions. This will give us a particular solution. Substituting back in, we have the velocity as a function of time is negative 32t plus 64. But let's not forget, our goal is to find the position function. Position will be the integral of this velocity function. So position as a function of time will equal, we're going to use the power rule of integration. So I'm going to leave the negative 32 sitting there unchanged for a moment as I increase the exponent by 1, which will give us t squared, and then divide by that new power, so divided by 2. Meanwhile, the integral of 64 will simply be 64t. And right now, we still have the constant of integration c. So we can simplify this a tiny bit by writing the position function as negative 16 t squared plus 64t plus c. Once again, let's see if we can use the initial conditions to convert this from a general solution to a particular solution. Okay, we are told that the initial height is 80. All right, so that's an initial position. In other words, s at 0, the position at time 0, is equal to 80. Let's substitute that into our general equation. So at time 0, so we have negative 16 0 squared plus 64 times 0 plus c. So at time 0, the position is 80. So this entire expression is equal to 80. Of course, here again, because we are substituting in 0, both of these terms now have a value of 0. This immediately tells us that 80 is equal to c, and we have the constant of integration that matches the initial conditions. Quickly substituting this back into the general solution, we have the position function we were looking for. S at t is equal to negative 16t squared plus 64t plus 80. Note that when you're dealing with projectile motion, the position as a function of time will always be given by 1/2 gt squared plus v sub 0 t plus s sub 0, where g is the acceleration due to gravity, negative 32 feet per second squared, v sub 0 is the initial velocity, and s sub 0 is the initial position. So in other words, you will always find the initial velocity right here in the equation, and you will always find the initial position right here. And because of the acceleration due to gravity, you will always see a negative 16 right here. Let's take our analysis one step further and ask ourselves, when does the ball hit the ground? Well, if the ball is hitting the ground, that means that the position is now 0. So, in effect, we have to set the position function equal to 0. So we have negative 16 t squared plus 64t plus 80 equals 0. I'm noticing that all of these coefficients are divisible by 16. So let's divide everything by actually negative 16 so that we will have a positive leading coefficient. So this will give us t squared minus 4t minus 5 is equal to 0. This looks like it would be pretty easy to factor. So let's go ahead and solve this by factoring. So let's see, t squared is t times t, 5 is 1 times 5, and with that negative 4 in the middle, we will need a positive 1 and a negative 5. So we factored it. Using the zero product property, t plus 1 is equal to 0. That will give us one solution. And t minus 5 equals 0 will give us another solution. Subtracting 1 from both sides, we have t is equal to negative 1. And adding 5 to both sides, we have t is equal to 5. Keep in the back of your mind that t represents time. How much time has elapsed? So in this context, we cannot have negative time. So the t equals negative 1 is extraneous, and we will ignore it. So when will the ball hit the ground? At time t equals 5. In other words, the ball will hit the ground 5 seconds after it is thrown.